So today we'll talk about diodes. So diodes is a very interesting device, solid state device. What it does is, it's a two-terminal device. So what it does is it's a one-way conductor. When we put it in forward bias, which means the positive terminal with P side and negative terminal with N side. So it has two parts, P and N. We call it PN junction diode. That's a full name. So when we put it in forward bias, it acts as a conductor, which means the current flows just like it flows through a resistor. And the current is calculated as, so there is a formula which is ID diode, it's given here, equals IS e to the power Vn over NVT minus 1. So if you see, there is a couple of things here in this relation. It has an exponential dependence on the voltage and temperature. Now, IS is what we call as reverse bias current. This N here is what we call as ideality factor. From the ideal diode, there's always difference from an ideal diode. So that is what's covered in this factor N here. Now, when we put it in forward bias, it's a simple circuit. We have our load, and we have the diode, and we have the voltage source. So we're talking about DC for now. In the forward bias, it just acts as a short circuit. So the current just flows. In this relationship, the thing KT by Q, which is VT, we write it as VT. It is a constant. So its value is 26 millivolt or 0.026 millivolt. So here, this VT thing, the formula is nothing but KT by Q. KT by Q is Boltzmann constant times temperature divided by electron charge, a unit electron charge. So it's a constant. So we just use it as 0.026 volt or 26 millivolt. So this is what goes, so VA is the applied voltage. So which means the current has an exponential dependence on the applied voltage up till after some time. So when we turn it on, we have to crank some voltage before it really turns on. In reverse bias, the current is just minus IF. So we use the minus to show that this is the minus current. It's the reverse bias, and we show it as minus voltage. With the minus voltage, when we plot it, we show it as minus current. And this is generally a very small current, picoamp, so we ignore it. So we call it that it's an open circuit. We don't even consider it as current until a certain voltage. So there's also a part to the reverse bias also. If you crank up into a very large reverse bias, then it starts conducting in that direction as well. But we'll look at that. Now, what is a PN junction? We said here it's a PN junction. PN junction in solid state devices, the devices which make up all of our electronic devices, semiconductor material. So it's a semiconductor material. Semiconductors are materials which are not very good conductors, and they're not insulators as well. So their conductivity lies somewhere between insulators and good conductors. Good conductors, we generally call them metals, but there can be other materials that can be good conductors as well. So what it says here, that the metals or good conductors are aluminum, copper, gold, and insulators are ceramics, wood, rubber. But semiconductors are materials like silicon, germanium, gallium arsenide, which their conductivity lies in between these two, unless we add some impurities to that. So impurities, we call them impurities, we call them dopants. There are many ways, different ways how we do that. So when we add in a pure silicon material, and it's not just silicon, it is crystalline silicon, single crystalline silicon. Same for germanium and for other material. So it is a crystalline material, and when we add dopants, so we add other materials from either group 5 or group 3 from the periodic table. Right? So silicon is group 4, like carbon, but we can take some dopants and we can, like aluminum, and we can add small amount to silicon, and that they make silicon a good conductor. Now, they're adding, so different materials would result into different kind of semiconductor. For example, if you add a material that results into excess of electrons, we call that kind of semiconductor to be N-type semiconductor. But if you add a material that causes excess of holes, holes is we take it as a positive charge. Hole is basically absence of electron, but we count it as a positive charge. So if we add a dopant which would cause many more holes in it, we call that as P-type material or P-type silicon or P-type semiconductor. In both cases, it is, we know precisely what is how many electrons are there or how many holes are there. And we use specific formula to do that. In an intrinsic semiconductor or a pure semiconductor, pure silicon, we know how many atoms are there in 1 centimeter cube, for example. So from those atoms, we know how many electrons they would contribute. So we know, like here it is showing Ni equals 1 to 1.5 times 10 to the power 10. It is nothing but it is telling us that there are this many electrons in 1 centimeter cube of silicon, an undoped silicon, a silicon where intrinsic, where there's no doping as done. But then we do doping, so we know how much doping we are doing. For example, if we do P-type doping, we would know, we call it Na, that's the number of acceptors. So P-type dopants are also called acceptors. And this would tell us the hole concentration. And using this, we can find out electron concentration as well using this formula. So in this formula, we know Ni, which is the concentration of intrinsic semiconductor. Na is what we are adding to it. So if you know those two things, we can easily find the amount of holes and electrons in that semiconductor material. So let's move on, because if we know one type, it's the same thing for the other type. If we know doping with aluminum gives you P-type, then doping with phosphorus gives you N-type. But the calculation principle is the same. In this case, P is what we call as concentration of hole, and N is what we call concentration of electrons. Na is the concentration of the dopants. In this case, it's acceptor. In this case, we call it donor. Not the donor kebab, but donor as the concentration of the electron donating species, which is phosphorus in this case. So we know that. So from that, we can find the concentration of holes. So the idea is we have a material which is P-type, which has many more holes, a material which is N-type, which has many more electrons. We bring them together, and that forms what we call PN junction or a diode. So in these devices, both holes and electrons, they both contribute to the conductivity of a diode. Now, we said that in forward bias, it conducts. In reverse bias, it does not conduct. So this is how it would look like in graphically if you put it like this. So which means that you crank up voltage in forward bias, nothing happens up to certain voltage. We call that voltage V in, and after that, there's an exponential increase like shown here. Now in reverse bias, this has to be a little bit like no current, almost no current for a long, long voltage. And then it should show like this. Because this voltage is just half voltage and this breakdown occurs at a much smaller, much bigger voltage in reverse bias. But nevertheless, it just gives you an introduction here. That's why we can go with this, how it is shown here. So the idea is that when you turn it on in the forward bias, you have to crank up about 0.5 to 0.7 volt before, and we call it cut-in voltage, before it starts conducting in the forward bias. And until then, there's very small current, but after that, we start getting high current. And on the reverse bias, we have to crank up for a long reverse bias voltage before it starts conducting. And then at that time, it starts conducting to large extent. It becomes almost short circuit. And we call that breakdown voltage, after which the diode just starts conducting at a higher voltage. Right? So we can use a resistance to limit how much current it flows through it, because we don't want it to burn. So we use some circuit with that controls how much current can flow into the reverse bias condition. So if this breakdown is much steeper, like here it is shown to have some slight angle, but if it is much steeper, straight down, we call it a Zener diode. So that's a special kind of diode where the current is huge in the reverse bias once it reaches the breakdown voltage. All right, so just basic introduction. Now we'll start putting into a circuit. When we say it's forward, it conducts in forward bias and it does not conduct in reverse bias. It has a good application in when we are using AC current. So why? Because AC goes positive and negative. We can use that to rectify. Rectification is a process where we convert AC to DC. And there are two types. We have half-wave rectifier and full-wave rectifier. We'll look at those. That's part of this lab. When we just look at the model, a DC application would just show a load, the voltage drop across the diode, the current passing through the diode, and the total voltage, DC voltage that's applied into the whole circuit. So we write, when you see VDD, that would always mean the voltage source. And when you see VD, that would mean the voltage drop across the diode, right? So and ID would be the current that flows through that. So if we know these basic terminology, that we have a load resistance, this is the voltage drop across the diode, this is the current through the diode. Now what we are doing here is we are taking this forward bias plot of current versus voltage, and we are superimposing on top of it another behavior of the diode, which just shows that there is a maximum current that would flow through that, and that current would be the voltage supplied divided by the load. So of course, in this circuit, there is a maximum current that can flow. So that current would be from Ohm's law. If we just take V equals IR, we can write it in terms of I equals VR. So we get this point of current that can flow through that diode. And on the x-axis, we have the voltage. So we have a point of what is the maximum voltage that can pass through this, the whole circuit. So we get 2 points, and if we connect those points, we get what we call as a load line. So load line tells us that the current can stay only on this value throughout the operation. It cannot go anywhere apart from that. And this gives us a point, what we call as Q point, the operational point for a diode, because the current cannot possibly go above that. So this is the point at which the diode will be operating. So this is what will give us the voltage drop across the diode and the current that will be passing through that diode. So in case of DC, we get this load line and we superimpose that on the characteristic curve of a diode, and that gives us the Q point or the operational point for the diode. All right, so far with me, how do we get load line and how do we get the Q point? So Q point, the operational point at which we will run the diode. Now, when we say there is a current that's associated with diode, we can, and there is a break-in voltage, which is half volt. So we can also model that something like there is a reverse. So whatever voltage we are applying, a diode is applying a voltage opposite to that, up to certain point, up to 0.5 volts. So how can we model that? We can show that as another voltage source in the circuit, which is shown here as VTD. So the threshold voltage of the diode, which is in opposite polarity to this power supply. And we are just modeling that. We say, okay, this is what is giving you that 0.5 voltage, as we saw above. That voltage until what time? Until that point, the diode doesn't start conducting, right? So we say, okay, that's the voltage which is supplied by the diode itself, just for a model. And hence, there is no current flowing until the VDD becomes bigger than VTD. Does it make sense? So VTD is that break-in voltage or threshold voltage. The source voltage has to overcome that before the current starts flowing through the diode. And diode has its own resistance, has its own potential drop. So this is just that showing in this picture. All right, so, but now this was for DC, all good. Forward bias, short circuit, reverse bias, no current. But if you keep on cranking, then breakdown, right? Now, for alternating current. So alternating current is nothing but a current that's continuously changing direction, right? So it's going positive, it's going negative, which means in the positive cycle, the diode would be forward biased. It would be conducting current. In reverse bias, it will not be conducting, all right? That's one thing. Another usage of that idea is what we call as clipper circuit. So clipper circuit would mean that we would not let the current or the voltage that's applied to go beyond certain value. So that means that if you apply an AC, which is riding on top of a DC, so there is a DC component to it, and then there is an AC that's running on top. So we would clip it to go beyond certain voltage on both sides. So we can restrict how much voltage can go through this circuit. So diode can itself become what we call as a clipper circuit. It can limit and or cut off how much voltage can pass through, because it would be reverse biased on those locations. So that's one application what we do for a diode. We use it as a uh, clipper circuit. The another thing what we do is it's called clamper circuit, which means that we can, if there is a signal which is between +4 and -6 volt, we can use a diode to bump this up, and the difference of these voltage, which is 10 volt, can show up as going between 0 and 10 volt. So what we have done is we have taken the minimum up and clamp it there. So that's why we call it clamper circuit. So these are two kind of circuits that we use. These are two examples of, there are many ways where we use diode, but these are two basic examples where we use them to either restrict the voltage that can pass through to the next circuit, or we can clamp a signal to a different DC level and move it up or down as we would want it to do. Now, coming back to the AC modeling. So in DC, it was just the reverse bias current times an exponential dependence on the applied voltage. But when we talk about the AC voltage, the signal, the behavior is slightly different, it's slightly more involved. But when we simplify the relationship, what we get is for small change in voltage, the corresponding change in current, delta I over delta V, becomes something of dependent on the temperature times kT by Q, which was the threshold voltage, 26 millivolt, 0.026 volt. So current divided by 26 millivolt. That's how this relation simplifies of how much would be the change for each small step in voltage, how much would be the change in current. So that would become the current divided by 26 millivolt. And if you model that, that behavior looks like this. So for small change in voltage, you have small change in current, but that value of current is something which is divided by a factor of 26 volt. So we call this dynamic forward resistance because this depends on how much current is flowing through that. So if you simplify this relationship, now what we have done is we have taken the Ohm's law, V equals IR, and from this we have written R, we're still denoting resistance. We have written V over I, and this is the small change in voltage that we calculated here. We have just flipped that, right? So coming from there to here, we call this the dynamic forward resistance, and that's delta V over delta I. So taking that relationship, we get something what is called kT by Q times I, right? So far with me, how we got from here to here. And from there, we plug in these value, we get 1 over 40 times I ohms as the dynamic resistance of a diode. So now this behavior is what we call small signal behavior, which means the AC is not very high amplitude, it's a very small amplitude. There is a different behavior when we deal with large signals, but we'll just stick to that how much is the small signal behavior. We get what you call dynamic forward resistance. And when you then model your diode like this, instead of the DC resistance, in that case, we use that small RD that we calculated from that relationship on next page. So in the small signal AC case, then we use RD instead of the DC resistance. All right. So just talking about modeling, or if we have to calculate something, how do we do that with small signal? All right. So another application for diode. Yeah, so another definition first. Peak inverse voltage, that's the peak reverse voltage when we reverse bias it. Right. So if you look at this relationship, this picture that I showed, there is, if you increase the voltage in reverse bias, there is certain voltage that it can maintain. The voltage is not going any further. Even if you increase the voltage, the current is saturated. So we call this voltage as PIV. We cannot go any further that voltage. Even if we do not get any change in the current. The current is already saturated. The current is already at higher level. So we call that voltage as PIV. All right, so far with me, everyone? There's some basic definition, and we'll soon get into building a circuit. But when we build a circuit, we need to know what's happening and what current is doing what. All right, first application, a rectifier. So what does a rectifier do? It diode conducts in forward bias, does not conduct in reverse bias. So if you give it an input signal, I'll come to circuit later on, but let's just, if you give it an input like this, you're going to get an output like this, which means it is removing the negative part. But what it is doing during that thing is it is completely removing, which means it's giving us half signal in the output. So we call it half wave rectifier. It has got rid of half wave. Well, for us, what does it mean? Are we losing our signal? If it was just a diode, yeah, we would lose our signal. But what we are doing is, in the circuit, we are using a capacitor. And let's come to the circuit first, and then we'll look what's written above this. Now, what's happening here? Let me make this a little bit bigger so we can see the thing that's. These are the things you can do with the Apple computer. Just with 2 buttons, you can do stuff. So now, just let's follow the signal and see what happens during that process. So I'm going to use red for this positive side. So in this part, what's happening is this is forward bias, right? That this diode is forward bias. So current is flowing this way. And in the meantime, this voltage is this capacitor is parallel, right? So the capacitor is getting charged up. It's accumulating charge while the current is flowing, but because it's being in parallel to this guy and the load, it is charging, right? So at the end, we are getting the signal and we are charging the capacitor also. All right, so far so good. Now, let me use another color. Let me use a blue color. In this part, what's happening? In this part, this guy is reverse biased, which means there is no current flowing on this side, right? So I'm going to make blue and I'm going to say no current flowing on this side, right? But now this capacitor, which is here, will start discharging. The current will flow from here in the circuit, right? So what we would get in the output is now we would get some current flowing like this. And the capacitor is discharging, the current is going down. You're with me on this? Paula, make sense? Isaac? Andres? All right. I come back to the red one. So red means this guy is coming, which means now here the current is already here, so current will start going down again. And we will encounter the reverse bias by then, and we will start seeing a capacitor discharging again. So what we get is, when we have a half-wave rectifier, what we get is, we get this behavior where the output is composed of the positive side, and then capacitor takes over, current still flowing, then the positive again picks up, then again negative, capacitor picks up. So we get a signal at the output, which is still current is flowing, not as good as you would want in a DC signal, but still something is flowing on the positive side. So what it has done is, it's called half-wave rectifier, because instead of just cutting off everything like this, what it should have done without capacitor, we put a capacitor and we are getting a signal. So we are getting a rectifier, but just half-wave rectifier. Does it make sense? So rectifier is a device that converts AC to DC. That's what it's supposed to do. So we are getting rectifier, but our rectifier is only working in the positive half wave, and then capacitor picks it up. So we get a signal, good enough, maybe good enough, we'll see. So now that's what I just showed you in red and blue. That's what's written here in English. Positive half cycle of input wave, diode is forward bias, diode conducts. On negative half cycle, diode reverse bias. So this is talking about no capacitor. In this case, what it's stopping, so this is the case for no capacitor up to here. But the image is showing you with capacitance, so hence the signal changes from, instead of just this guy, we get this guy. All right. So what is the average voltage? So we are getting voltage, but it is changing. So there is a way we are getting voltage, average voltage is Vp by pi. Right? So we are getting the voltage coming from the input divided by pi. We can also find RMS, which is root mean square, which would tell you the ups and downs. So it will have the what you would see on an AC voltmeter. So that would be then Vp divided by square root of 2. What we call RMS value. So for a signal, remember, always we would be interested in average and RMS. So RMS tells you across a long period of time what is the power that's getting transferred through a circuit. So we use RMS a lot more than we use the average. Now, in this output, there are a few things to see. There's charging, we can see the charging going up. We can see the discharging. The VP is the peak voltage that it achieves on the output. And then the difference between the maximum and minimum, we call it ripple voltage. We write it as VR. Ripple, just like a wave going up and down, we call it ripple. So this is the ripple voltage, and this is the difference between the highest value and the lowest value, right? And if you look at it, so this now output is riding around this some value, and that's the DC voltage that you're getting in the output, right? So that's is the half of ripple voltage, what you can call as the DC voltage on the output. All right, so far so good. So now this is what's talking with the capacitor in the circuit, right? So I straight away, we talked about capacitor, and we can see if there's no capacitor, we would be not getting negative cycle. So what we would be getting is just half cycle. So now what is the actual peak output is written as VP out equals VP in minus 0.7 volt, because that's the time, that's the voltage it requires for it diode to start, right? So 0.5 to 0.7 volt. So that gets used up, and whatever is after that, that's the output voltage that we would get. So we subtract the break-in voltage for the diode to get the output voltage. Now, if you put a load, we can see what is the charge coming out from capacitor in time t. And that's a simple formula, Q equals IT, which is charge flowing from capacitor in time t. The current divided by time is the charge. So if you know current is the amount of charge flowing through a cross section in unit time, right? We know that. That's how we define current. So if you want to get the charge out, we just multiply it with time, we get the charge back that's flowing out of it. Why it is important? We're going to plug in the value of charge into the capacitance value. So we know from the capacitor definition, Q equals CV. We know that. So from this, we can write it. There's no dot here. So we can find the ripple voltage from this by flipping Q is equal to CV, and we would get Q over C. We plug in the value of Q, and we get this relationship for the voltage, which is nothing but Q over C, IT over C. So we know current, we know time, we know capacitance. But T is 1 over F. So for an AC signal, the time period is 1 over frequency. We know also that for frequency. So we plug in that, we get the ripple voltage in terms of the capacitance and the frequency of the input signal. So 1 over CF is the half wave ripple voltage. Half it. So which means we can exactly know how much is the, I'm just gonna remove this. So this means that we can know exactly what is the ripple voltage here. So how much is the difference going to be on the output in the highest and the lowest value just by knowing the frequency of the signal and the capacitance, right? So now, if the ripple voltage increases, if the signal is going through big changes, the output DC voltage will increase, because now if this guy becomes large, your DC goes smaller from than if it was small. If the ripple was small, DC voltage would be larger. If ripple is larger, which means the DC voltage will become low. So that is related by what we have seen here already, that VDC is equal to VP minus half of the ripple voltage. Are you with me on this? So here we know this is the ripple voltage, and this is the peak voltage. This is the ripple voltage, and this is the DC voltage, which is VP minus half of VR. Right, with me on this? So from this, we can see that if the ripple voltage increases, the DC voltage decreases. So that can be then, so we plug in the VR here, what we get is, we get the DC voltage in terms of the input frequency and the capacitance that is used. So by knowing what capacitors we are using, we can design a circuit for specific DC that we want on the output. Right? Now, how smooth is the signal is a direct factor of ripple voltage. So the ripple voltage, if that's much higher, we would have a bigger ripple factor. And we want a smaller ripple factor for smooth output. Right? So that's the relationship between what is the ripple factor. If this guy is large, this guy would be smaller, which means there'll be overall bigger ripple factor in percentage. So do you follow that? Let me make this a little bit larger so you can see what's going on here. So this will tell us how smooth is the signal. If this guy is large, this guy would be small. The overall percentage of ripple factor would be larger, which means the signal will be less smooth. But if ripple is small and DC becomes bigger, which would mean the signal would be going through smaller ripples. Signal will be smoother in that case. So you want the ripple factor to be a smaller number. All right, with me on this? Now, we want to make a full wave rectifier, which means that we don't want to use a capacitor and we want the whole signal in the output. The simple way to do, if you think about it, we provide two paths to the current. On the positive side, we provide a path where some diodes are in forward bias. And when it's the negative signal, we provide another path where some other diodes are in forward bias. But the end goal is we want to get a DC out of it. So how do we do that? So we want to conduct on both half cycles, on the positive one and on the negative one both. So we create this circuit. So let me do again two colors to show what happens in the positive side and what happens in the negative side. So on the positive side, let me pick red color. So on the positive side, they will go through this. And on the positive side, this is negative, which means the signal is going to negative. So this would be forward bias for that case. So what you get is a voltage here and a voltage here. Now, if it is negative, so this is this part, red is this part. Let me complete the circuit. So negative is this part. Are you with me on this? All right, now we come to the negative side and I denote it with blue color. So in this case now, this is high. For this would be the forward bias. And this is low on this side. So this is forward bias for this. Oh, sorry, it has to go straight from there. So what's happened is in both cases, we have reached the same positive signal on the output. On the output, we have got both high signals, whether it was red or whether it was blue on the input signal. So let me now clean this up, and now we can see the theory written for that to get a better idea. So what we are getting is on the output for both cases, we are getting a positive signal. And what we have done is, again, we have used a capacitor, because if you don't do that, then we would have been getting just this signal. It would have gone down and come up and gone down if we did not have a capacitor. But having capacitor, what happened? When it was going down, the capacitor picked up, capacitor started giving out the signal. Same case here, capacitor picked up. So what you get is, again, this Ripley signal on the output. All right, so what's happening here in a full wave rectifier on first cycle, when A is positive, D1 conducts to make top end of load positive. At same time, terminal B is negative, so D3 conducts to lower end of load. On next half cycle, A is negative and B is positive, so D2 conducts to top end of the load. So they are giving the same sync signal on the output. So if there was no smoothing capacitor, again, now this would be 2 Vp divided by pi. Before it was just Vp by pi, because we had one peak coming for full wave. Now for full wave, we are getting two peaks coming on the output. So hence we have 2 Vp divided by pi. All right. So similar way, ripple frequency is not twice, because before we were getting only one side of the signal. So it was half frequency, but now we are getting twice of that. We are getting 2 times than that. So we get ripple for full wave rectifier as 0.5 CF, same combination as before. But here it was I over CF. And now we have half CF. And VDC is now quarter of CF or subtracted from the peak voltage. So that gives us now for voltage, we have a slightly involved relationship, which is square root of the RMS value of R1 to 2. So we'll not get into that. You just have to know that there is a way to calculate ripple voltage here also, a little bit more involved than before. All right, so we know now what is the basic circuit of full wave rectifier as well. Let's start building on those. So what we'll do in this, and this posted already, we'll make the circuit, we'll put D1N4001. So you'll pick it up from the diode module. In PSpice, there is a diode module. That's what you will use. Now, you will determine the IV characteristics for DC. You'll just sweep from -5 to +10 volts. And you will set the increment of 0.1 volts when you set the linear sweep. Right, Umar? Umar, are you in public place or something? Okay, yeah, keep your mask on. All right, so same for Renee, same for Angel. I'm just gonna let you go, guys. It's been an hour. All right, so what we will do is now we'll be using diode and run the simulation, and we'll get the IV characteristics of the diode at the probe. So by changing DC, we will then do the reverse saturation, and we will get it to breakdown voltage. So keep on taking the voltage and you'll see there will be huge current that will come out. So those are the plots that needs to be saved for your report, right? And then what you would do is you would do the piecewise linear model where you would run different parts. So you'll get this information from bias point detail from setup, where now you will show the forward bias, the resistance of diode, the voltage of diode, the break-in voltage. So all those parts would then you will get from the bias point detail. You'll get the VTD as was shown in the graph before. So you will get by doing the toggle cursor button. So you pick one button near ID and you right click on the same point. And so it's given, the whole process is given how you would get those values. And you'll use this formula to calculate the threshold voltage of diode, VTD. And then you'll change to a Zener diode. Zener diode, where the breakdown is very steep, right? It's just short circuit. The voltage doesn't change. So we use Zener diode as voltage regulator because whatever you do, the voltage will not change. There's no change in the voltage. It's stuck at that current. So then you will use Zener diode B1N750. You'll repeat the same steps for that. 1 to 5. Here. Piecewise linear model for that. Then you'll implement a clipper circuit, which cuts off the values on both ends. So it keeps the value of the current in certain range, right? We don't want to overload our circuit with high current. So we use a clipper circuit, right? To keep the current in between certain values. So you will use this one to do what both of these diodes are doing exactly the same thing in reverse bias. They are keeping the voltage up to certain level. Oh, sorry, they're keeping the current up to a certain level. It cannot go beyond that. All right, so this is again where you will determine input versus output. You'll set it from 1 kilohertz to and 10 volt peak. So that will be your input. You run it and you will see what is the output input V1 and output for D1 and for D2. For clamper circuit, which is used to push the DC voltage up, this would be how you would do. Again with 1N 4001, and we will set the input 1 kilohertz and 10 volt. So you'll play with resistance, capacitance, and second voltage, and you will see the input and output across R1 from the probe. You change the voltage -4 to +4, and you will see what happens between those two settings. And the last one is diode bridge rectifier and regulated power supply. So exactly the thing which I showed you, bridge rectifier, the full wave rectifier, you will lay it out in this way. So here again, then, so you'll use this transformer, FRM linear, and you'll set L1 and L2, the windings to 100 millihenry, V1 to 10 volt, 50 hertz, and run the simulation. And you will see the waveform across the load, across R2. And that would tell you what is happening at the full wave bridge rectifier. So here then you will calculate R2 DC and RMS value, and you'll compare it with the theoretical value using those voltages and those formulas that we discussed at the start. And then that would be without capacitor, and then you will introduce capacitor, which would make it regulated DC power supply. So now the ripple would become smaller, so you'll get a smooth DC output voltage from this rectifier. All right,